All right, so I prepared a bunch, including the additional supplementary materials I have the department send over to you because I think they would actually make your job a lot easier to catch up on fixed effects. Not just this, but also difference, two periods, three periods one that we talked about on Tuesday afternoon. So I'll explain step by step, but this is acting funny because I'm just trying to load the data. That's it. But apparently the version thing, there's a different types of version. It works on my laptop. I have a Mac, so I'm installing the packages. It is restarting R as of right now. So let's give it a little bit for time. It should be fine. But if not, I mean, I can have you run on your computer. It's not like I have to run it on mine anyways. But I have the entire set of R codes for you. But I think which would be much more helpful than what I had prepared for you originally. I'll just be honest with you on that. So this is what I prepared for you before. This is a more standard introducing you to panel data. Why are we using fixed effects, that kind of thing. But this one, that what I found, well, I actually shared with you on Tuesday. I said, if you're doing causal inference for a living, particularly if you're doing research, if you're doing, academic writing, well, that's the same thing, research, academic writing, or teaching, or even doing industrial work. You could actually use one of this as a great resource for you to work on. I mean, this is more than most recent, and then the authors have a great way of looking at it. Okay, so what we are dealing with today is essentially we call that fixed effects because there are lots of uncontrollable variables that we wanted to deal with. Basically, there are observed variable when you are trying to identify the causal relationships between two, let's say between two variables, and you wanted to find out, what are the factors that would actually impact Y from happening. So there are a bunch of X's, and then there are observed variables. There are also unobserved variables. Most importantly, we call this like unobserved confounders because there are going to be, I want to say, we'll be looking at the map pretty soon. Like there's not going to be like a direct path or interdirect path, something like that. It's going to be a complete mess in a way. So how do we sort things out if we were to do that? So my plan for today is to do a couple of things. Okay, one. First of all, this is our workshop thing that I sent it to you originally for Tuesday. I'm going to hold down to that. I'm going to begin by looking at the supplementary material 2, which is what I have opened up right now. If you have it, you feel free to open it. If you don't, then that's fine. Bear with me, and then as we go through this, there are fancier slides that I choose not to use for now because I feel like I can do a better job just by using the typical classic old-fashioned way and going through this. Okay, but I promise this won't take terribly like a 3 hours, something like that. But I think once you understand how this is a very, I want to say, user-friendly approach to explain fixed effects and also random effects, and then you should be good with this, okay? And then my goal is that if you practice using R today, following the codes that they provided us with, and then you can replicate exactly the same thing, let's say using Stata, okay? If you are, I'm sure you're very smart. I mean, if you wanted to do Python, given that you're, I should do Python too. I'm not terribly old. I'm just like lazy. I don't want to touch on Python because I feel like also, but I was looking at machine learning too. That's just, people are using machine learning to help with causal inference too. I was reading a lecture, virtual lecture invitation by NYU professor at the Stanford School of Graduate School of Education. She's doing, Jennifer Hill, who was actually a professor of mine. She's doing causal inference using machine learning. I hesitated to touch on anything that's a little bit more intellectually advanced, like machine learning, Python. I just feel like I can hold on to that because there's much to do with R. I mean with Stata already. I just don't want to touch on that. Okay, there's also this R thing I picked up last last year, I feel like, oh my God, this is already a lot. But now that I think there's Python here available, it is not as difficult as I thought it would be. Okay, it's a steep learning curve, but you have to invest, I want to say, a couple of hours to get started. But once you do that, I think the learning curve becomes smoother, and then you can go faster as you want to. Okay, so but this set of slides is so user friendly in a way that it has 3 versions of data. We're going to try R, because that's the theme for today. Otherwise, I would do Stata, and then do Stata if you want to. I think it's also applicable in many contexts. And then finally, if you want to try it, you can do Python. Okay, so but I think having Python as a necessary skill set will help you in many ways. Okay, today's job market. I was teaching yesterday. Someone was showing me their job advertisement. It specifically says that we prefer people who have econometric language, statistical analysis skill sets, and then Python and I believe it says Python and not R, so I'm not going to lie about it. They said Python is a plus. Okay, so if you want to do that, then that's great. But this is one specific phenomenon that we're dealing with today, which is called fixed effect. Basically, the core is that we're trying to control for unobserved confounders. Okay, I'm sure you understand what is confounder. So a lot of this discovery to identify your research question by control for variables. That's what we're trying to do. We control for variable when we're trying to identify the research question, and we oftentimes start from like a diagram, and we want to figure out what we need to control for, and to control for it, and then perhaps the following, this is like in reference to what they have talked about, but you don't have to worry about it. So 2 big problems that we ran into when we are doing this kind of like controlling for the unobserved confounder thing. First, oftentimes, we can't figure out the correct causal diagram that will tell us what to control for. We don't know what to control for. This is a classic problem, okay? If you want to study, what makes you earn more by pursuing a degree from Hong Kong U or by pursuing a degree from University of Science and Technology in Hong Kong, I mean, you don't know. There are a variety of options. People always want to go to the prestigious universities, and it's more competitive. There's a I want to say more steady alumni network who could probably provide more resources for you if you know how to take advantage of them. But it all depends. But is it really it's true that if you want to earn more, then you would only go to a Hong Kong U school or Hong Kong UST, and then that's it? Not necessarily true. And people are saying that if you go to, there are a variety of different schools in Hong Kong U too, business school, social science, medical school, etc. If you're looking at the earnings, you just don't know what to control for in order to earn more. That's put it like as a simplistic approach. Like you want to earn more salary, what do you want to do? And second, what if we cannot measure all the variables we need to control for? In either of these cases, we cannot identify the answer by controlling for stuff. So to find out the causal question, the answer to the causal question, we don't have enough things to do in order to do that. So fixed effects, okay? Fixed effects is a method of what we call controlling for all variables, okay? But how do you control for all variables using fixed effects? That's kind of like, I want to say, a big assumption we are holding, but this is also something, whether you are observed or not, as long as they stay constant within some larger category, that's the key, some larger category, then we can do that, okay? And pretty simple too. We just control for the category itself. We call that fixed effects. And in doing so, we control for everything that is constant within that particular category, within class variation, for example, okay? There could be a lot of confounders impact, let's say, students coming from different schools, like, I'm pretty sure that you're all very charismatic, and I assume that the majority of us coming from faculty of social science. So you might be you certainly have different pursuits than students from the School of Public Health or medical school. That's a professional specialized school, or the Faculty of Business Economics. Sure, you're all charismatically different, but if I want to control the individual differences, like how does your personality may impact your earnings, then I can control the entire faculty, okay, the entire school as a whole. So I control everybody's individual differences. There's no way that I can measure your characteristics at all whatsoever, okay? Because you all, I guess, there are different personalities. People say there are 5 different types of personalities. I don't think that's the case. I think there are more than probably 50 different types of personality, depending on how narrowly defined you want yourself to be, okay? And your personality changes along the way too. So it's really hard to control. That being said, if you control the category within that particular category standards, well, it's arguably not, okay? So there's, again, in causal inference, there's only so much so that you can do. So that's, what we hope to achieve. So what does this mean for a variable to be constant within some large category? For example, let's say that we're looking at the effect of rural town. This is a specific example, okay? And bear with me on that. While I read this through, I just want try to make this make sense for you. So let's say that we are looking at the effect of rural towns getting electricity on their productivity. An obvious backdoor is geography, okay? What do you mean backdoor? Okay, let's hold on to that thought. Rural towns up in the mountainous hillsides will be more difficult to electricity, and also might be different in the productivity for other reasons. So that's kind of like, I want to say, the setup or the circumstance that we're in. However, geography doesn't change a whole lot. If you observe the same town multiple times, it is likely to have the same geography every single time. So what if observing the same town in many different years, we control for town, meaning that we are doing fixed effects for town. So whatever that geographic effect would be, rural towns or downtowns, or however geographic distance you want to define it to, you control the entire thing for the town. If we do that, we'll be removing any variation explained by town. And since there will be no variation in geography that isn't explained by town, that's it. So there are too many variations with town, the specific variable itself. Instead of controlling for many variables within the category of town, we control just a couple of them and call it a day. Okay, so now in this case, we probably could have measured and controlled for geography, no big deal. But what about the stuff that we cannot control for? Just to give you one example, as it says here, there are lots of social science context where we want to control for a person's, well, that's what I said, like a person's background or your personality. That's like high dimensional thing with lots of aspects we can't possibly measure. It is just unobserved. If I ask you, hey, are you a moody person, you probably be wondering, I don't want to tell you that, because even if I'm a moody person, I don't want to share that information with you because it may work for me or work against me. I don't want to reveal too much about me. That's smart, that's fine. So, but that's what I'm saying. This is going to be hard to control for. That being said, these type of high dimensional or high stake characteristics of the specific person with lots of effects we can't possibly measure. It's because it's unobserved. So we add fixed effects for individual person. That's what we control for. Okay, we can do that individual level per fixed effect. We can do that. So fixed effects, therefore, fixed effects can be thought of as taking a whole long list of variables, however many you want to imagine them to be, on backdoors that are constant within some category, and collapsing them to just be in that category, and then controlling for that specific category and say that everything is going to be constant in the geographic variable town, for example, including person's backgrounds, those high dimensional characteristics. Okay. So again, followed by an example, we say that we're interested in the effect of a visit from the German chancellor on the country's level of trade with Germany. So let's look at it in a supposedly causal diagram. Okay, so this figure, we are trying to figure out this question, like the causes of trade with Germany, and then we're trying to look at if their, head of the state, the chancellor, would actually visit, then is that going to impact the other particular country's trade amount or volume of trade with Germany or not? So this is what we're trying to identify. There are many variations across this in this diagram, because this is the truth. We essentially want to find out this straightforward, causal effect. Does a chancellor's visit impact the trade with Germany positively or negatively or not. So this is what we want to find. But we also have to bear in mind that there are lots of other factors associated with this diagram. It is not going to be a straightforward path whatsoever. There is going to be the history with Germany. There is going to be the current politics impact. There is going to be the culture, population. There's going to be geography. There are going to be many of them. Okay. So if you want to ask me this question, hey, Secretary of State of the United States, Anthony, I forgot his name. Blinken is visiting China these days. So he visited NYU Shanghai yesterday. He's in Beijing today. Does his visit will solve, let's say, a certain set of problem for the U.S.-China relations? Okay. Well, we have to factor in factors such as this: the current politics, geography, history with, with the U.S., cultural population. Well, obviously the U.S. and U.S. people and us are very much different. For folks like me who lived in both countries extensively, I can testify that there are lots of differences. The way we think, the way we act, the way we consume things, etc., are going to be very different. So there are going to be lots of reasons that are going to help us explain this phenomenon. Chancellor's visit, is that going to cause the trade with Germany to go up or go down? We don't know about it. Okay, so in the diagram, okay, there are quite a few causes of trade with Germany, many of which could be difficult to keep track of for sure, even not to mention to measure them. So, for example, the culture thing. How do you measure culture thing? Okay, you can survey people, but that's going to be very much limited. There's just like it's impossible to take account into every single factor that's going to impact the trade level with Germany with that particular chancellor's visit. Okay, so however, what we can do is that we can note that several of these variables, the country's geography, the culture per population, the history of the country with Germany, are going to be constant within country, or at least they are not likely to change much within the span of any date we have. So we can redraw the diagram from 16.1 to this one. Basically, what we're trying to do is that we're trying to simplify the diagram by, narrowing down the causal path of factor X on factor Y. That's what we're trying to do. So instead of looking at a complicated diagram such as this with so many variations involved, we are simplifying this into four, let's say, specific variables. So we're looking at the impact of culture, population, geography, everything into a history with Germany. Now we are coming down to four of them. So what we're doing is that we're actually holding control of culture, population, history with Germany, current politics, etc. We hold that as an entire category, and we are trying to use what we call today fixed effects to control all of them all at once. So we simplified it to this, but this is not simple enough, because essentially we're just trying to identify the effect of Chancellor's visit on the trade with Germany. That's it. But there are also variations that we have to consider, which are current politics and also specific country that you're dealing with. So there are still more than what we want to have. So if but anyways, we have a simplified cost of trade with Germany for now. So with the simplified figure, okay, we can identify the effect without needing to control for each of the variable. We just control for the country instead. So that's a country level fixed effect, just so you know. Okay, if you still don't know what I'm talking about specific country fixed effects of just bear in mind that it is going to be a category level control that's supposed to control every mini details that would be occurring within that particular category. That's it. Okay, so for now we have looked at two examples. One is on the country level, okay, and the other one we said is on the it's on the geographical level, like the town level. Both are locations. Well, countries, towns, both are locations. Okay, so what are we doing with? Okay, what are we doing with when we control this country level fixed effect? So we know this. By saying we control them at the country level, it doesn't mean that we have collapsed everything into the country level. We haven't collapsed everything into the country. Anything like to change regularly over time, like the current politics of the country, won't be addressed by fixed effects, because that is going to. So you have to think clearly when you're trying to set up a causal framework or mechanism, you have to think very thoroughly about factor, what are going to be controlled with this fixed effects, what are not going to be controlled with this fixed effect. You can control them at different levels, the geographic level, the country level, which is similar to some extent, but you have to think about what are not going to be taken care of by controlling the country level fixed effects. So if we want to identify this effect, we still need to control for current politics in addition to fixed effects for country, and that is fine. Okay, you don't have to have fixed effects for everything. Okay, but you can have fixed effects for certain types of things, like class level. But the thing is, you really have to understand that by applying fixed effects, not only we're going to do so, let's say, in application using R, but I think the key for today's causal inference seminar is that you actually know what you are controlling for using fixed effects. So you are able to you're able to explain your story in a better manner. So that's what I'm trying to work with you today to have you take away. Okay, so the variation within fixed effects is in essence control for individual, whether the individual in a context means a person, company, school, country, or so on. What this means is just get rid of any variation between individuals. You're controlling, let's say, the within group variation. That's it. Okay, so and we know this because what it means to control for individual, and we take all the variation in our data explained by the individual and get rid of that. Okay, so you can essentially you want to find out if there's going to be exogenous variation to help you explain the causal effects, but with this controlling for the variation on individual level, by individual level, it can be country, town, specifically company, school, country, and so on. You do that, and then you get one step closer to identify what we call exogenous variation. That's kind of like again what we hope to achieve by using fixed effects. Okay, but it's not going to be that simple. Otherwise, our jobs will be done quick and easy. Okay. What's left here is variation within individual. What is variation within individual? Let's take a look at that. For example, let's say you are fairly a tall person, and we are gonna track your height over time. Okay. Which is I want to say a kind of like cliche but classic problem too. The fact that you are taller than other people is between variation. Okay, this is like between individual variation. Comparing you to someone else, you are generally taller or generally shorter. However, we can also observe that as you grew from a child to an adult, your height changed over time. Comparing to your shorter, younger self is within variation, something called within individual, and that's what we are picking up using fixed effects. So we control within, but not across variation between individuals. So the idea, again, the idea of fixed effects is that by sweeping away all the variations between individuals, we've controlled for any variable that are fixed over time. So time, we call that time invariant in a way. Okay. For example, no matter where I move in life, I will always have born in the same city. That's never going to change. The same goes for everybody else. So all the variation is the city of birth is between variation, okay? Between individual variation. If we, if we get rid of between variation, we've gotten rid of all variation in this particular variable called city of birth. And thus we controlling for that using what we call like a fixed effect. So one thing to note about this is that we really have got rid of between variation. Okay, that's what we aim at doing. So if we, if between variation is what we are interested in, we want to know the effect of the city of birth, then we can't do that with fixed effect, because fixed effect is just going to control individual level specific effect. And then if we want to know the effect of city of birth, then what do we do? Okay, then what do we do? Let's walk through this two technical examples of this. Okay, one of them with a table, the other one with a graph. So this is a table, and then we'll have a graph soon. So for this table, let's say we're interested in fact of exercise on the number of years, number of times a year you get a cold. Like basically, we're trying to study the effect of exercising on your health condition. Okay, so for subject in our study, we have you and me. Let's just simplify that. Okay, we have individual level you and me only, and then we suspect there are some variables like genetics that are fixed over time, so we can control that on the individual level, and then we can adjust for that with fixed effects easily. let's say we look at this data and we exercise. So very simple, 3 columns. This is very simplified, 3 column exercises and codes. So your individual level variable are going to be you and me, or a third person, or let's say you could add up, but this is just to simplify 2 people. You have 2 years, 2019 and 2020. Okay, you have the number of exercises that you do. All right, so this is kind of like giving you baseline level descriptive statistics. Now, that's the raw data, exercise measured in hours per week, how many hours you would exercise per week, like 5 hour, 7 hour, 4 hour, 3 hour, etc. So I mean, 3 hours a week is decent. I mean, but probably people would never move. That's also, I mean, not uncommon. 7 hour, I mean, if you're talking about athletics, I mean, they probably move, I want to say 7 hours a day, or that's not an exaggeration. But anyways, so this is the raw data. And then to get our within and between, so we need to get 2 types of variation. We need to get a within variation, which is, which is inside you, individual level. We also need to get between variation, like, across you and me. We want to get that variation. We need to get the within individual means. What do I mean? Okay, let's look at this specific table. So again, we had 3 columns to begin with, individual, year, and exercise. Now we are adding on 2 additional columns, which are the 4th column is what we call the mean exercise. Okay. The mean exercises, and then the within exercises means the difference between exercise and also mean exercise. So this is, we take the mean of exercise individual, given that this is only 2 years. This is to simplify the idea. You can, of course, include many more years. And in reality, you have many more years. All right. So for individual and subtract that mean, the difference between individual and in the mean is the between variation. Okay, this is what we consider as between variation. So the between variation for exercise comes from comparing your average 6 hours per week against 3.5 hours against my 3.5 hours per week. Okay, so this is kind of like looking at the differences between variation. The within between individual is the mean between variation, but the between variation between you and me are going to be your my 6 hour compared with your 3.5 hours. Okay, so if we subtract out those individual means, we are left with in ways we vary from time period to time period relative to our own average. So that's the idea. Now, why are we talking about this? This is what we call the within variation, looking at how things vary within individuals, okay, which is us. So my within variation exercise compare the fact that in 2019, I exercised half an hour per week more than average, which is this one, average. But I have 2019 exercises more than the average for half an hour per week. And then in 2020, exercise half an hour per week less than the average. So this category, we can put this in a graphic as well. Okay, so all right. All right, so here is what we will see if we actually put it in a graph. Okay, I'm going to scroll down a little bit so you can see the charts a little bit more clearer. Okay, so this is better. Okay, so this is better. So these are the 4 graphs we are looking at right now. We want, or these have already been drawn for you, so we want you to see this a little bit more clear. So we have what we call the raw data. On the y-axis is going to be how many codes you catch per year. On the x-axis is going to be the number of hours exercise per week. And then there are 2 individual level observations, me and you, represented by different symbols. One of them is a triangle. One of them is a solid dot. So you can see that. And then with individual means, this is what you would be able to observe. And then we observe between variations of you and me, and we observe just between variations just for me. This is what it is. Okay. So The top right, which is this one, okay, takes raw data and adds some individual level means, sort of like each of us getting their own set of x's. We find the mean exercise, a mean number of codes for you, and draw a set of x's at that point. So we see that. And 0 and 0 on your graph. Similarly, we draw sets of x's where my means are. That's 0 and 0 on my graph, okay? Of course, our shared graph, it's not 0, 0 for anyone. It's our individual means on both the x and y axis, okay? So bottom left, which is this one, bottom left was this one. Just like those axes, we put a point on the center of those axes and ignore everything, but those are individual means we're talking about, okay? And then we compare them, say, drawing a line from one to another. Then we are looking at what we call the between variations. What do you mean between variations? The variation between you and me. Okay, but the between variation could be expanded to more than just two people, okay, you and me, in many real scenarios, okay? Lastly, in the bottom right, we forget about you for a second, just focus on me. We zoom in my set of axes and call this axis 0 and 1, 0 and 0, and then now we can see that everything is relative to my own mean. Take that point to the bottom left, for example. Yeah, that's right. Okay, so oh yeah, right. So this is just I got confused for a second because I thought this was looking at just like you and me, but this is taking away you, just looking at one specific variable. So everything is relative to my own mean, and to that point on the bottom left, the top right, the point was above. So you get 3.3 hours per week, and then for me, that is like 5.5 hours, 5.5 codes per year. But in the bottom right graph, everything is relative to my own mean. So instead of 3.3 and 5.5, it's about 1.3 fewer hours exercise per week than my average. So anyways, you do all of this, calculation to actually perform fixed effects. We then take your set of x and slide it over on top of mine, and then see if that works. So that's basically the interpretation of fixed effects in a nutshell. What it is, okay? And then, but now moving on to this realistic question, okay? Moving on to this realistic question, how do we? What do we actually do? What does fixed effects actually do with to the data? Okay, well, basically it's the same as we control for a categorical variable. We are isolating the within group variation, so we find the mean differences between groups, individuals, and subtract them out, and that's basically it. So that's the fixed effects we're looking at. So again, just to repeat myself, we find the mean differences between the individual groups, or individuals or groups, and then we subtract them out. That's it. So we can look at this in a little bit, but just to give you a heads up, we begin in our raw data, noting that we have several individuals in there. In particular, we're interested in the effect of health eating reminders on actual healthy eating. That's another problem we're looking at. Our 4 subjects have each downloaded an app that at random times reminds them to eat healthier. They've chosen how frequently they want reminders, but don't control exactly on which day they come. So as I want to say, empirists who study random control trials, we recorded how often they get reminders and also scored them on how healthy they actually eat. So we have variation over time. That's number 1. How intensively each individual gets reminders, and variation in their healthy eating. There might be some individual level backdoors that led them to choose their frequency, and also which is what we call confounders, and also their general healthy eating level. So we still want to use fixed effects to close those backdoors. So basically, that's kind of what we want to do. Looking at this graph really quick. So again, on the y-axis, it is what we are interested in learning about, which is the healthy eating scores. So you quantify that. You want to measure how healthy people eat, and this is how we quantify that. And there are 4 people we are measuring at this time, or we are observing at this time. Me and you, 2 other persons, Li Qing and Shema. So we're looking at, and then on the x-axis, we are looking at the x variable, which is intensity of reminders. Doesn't specify which day, but we specify how many times you want to be reminded for different people. So there's a small positive correlation, as we probably can identify, between reminders and also the more reminders you get, and then the higher of the healthy eating score. So that's kind of like, I want to say the observational result. More reminders means eating healthier, but maybe the message are effective, if only a tiny little bit. But of course, we haven't identified the answer to our question yet, since we know there are individual based backdoors. So people may do things very differently. So we want to start a fixed effects estimation by calculating the mean reminders and the mean healthy scores for each and every one of our individuals to begin with. Okay, so if we look at the individual means, we have 4 of them. These are 4 of them, 4 individual means. Okay, so clearly a negative relation between reminders and healthy eating for the individual means. So if you look at that big score, they seem to follow a downward sloping curve, which is not going to be positive relation. Then the implication is that the between part of the relationship is actually negative. The people who choose more frequent messages are the people who tend to eat more poorly on average. So the between variation is going to be like if you just look at their individual means per se, then this is going to be a negative relationship. All right. So our next task is to remove any variation between the individuals, so that we can evaluate the effect over average effect across the 4 people. So we're effectively going to take all 4 of those positive and then slide them on top of each other. And then if we zoom in each one of the 4 individuals within variation alone, this is what it is looking like. This is what it is looking like. Okay, so this is me, this is you, this is Li Qing, this is Shema. And then each of the 4 graphs, the data is centered at 0 and on both x and on y axis. So now we put all 4 on top of each other. They're hanging around the same part of the graph. We put them on top of each other, aligning with all the positive signs, and we see this is where they are. And then this exhibits the within variation in intensity. This is a within variation scores. So with different individuals move on top of each other, we see a more clear picture emerging with a positive relationship between the intensity of reminders and score. So it changed from the negative relationship to the positive relationship between intensity of reminders, because we are now able to kind of like put them on top of each other and then identify more clearly of what the correlation is. But again, while the correlation in the raw data was very, very small, the within variation is that much, that 0.3, much more positive. And then since this is a positive relation, indeed is actually correct. So if we want to following this, if we want to find out how is it performed specifically, we could also decompose fixed effects. Okay, so this is a conceptual idea of how it worked. Okay, just to repeat myself, the way it works is that you stack them up, you look at the within variation first, and you subtract it out from the average between variation, and then that's how fixed effects works specifically for the observations. Okay, now if we look at how fixed effects regression generally work, there are a couple of steps, but they don't look very much different. They are similar to what we have always been looking at before. Just a typical regression. Fixed regression generally start with regression equation. Looks like this. Okay. This is a standard regression equation with 2 main exceptions, just like a standard one. X is going to be has the subscript IT indicates the data varies both between individual and over time. So this is going to change on two levels, the individual level and also over time. The second is intercept beta I is now going to be representing a way of fitting a straight line, but this means all the individual in the data are constrained to have the same slope. So there's no I subscription beta 1, but they have different intercepts because they are representing different people, and different people will have different, I guess, different intercepts for sure. So with this, there are going to be three obvious questions coming up with, using fixed effects in the typical regression, okay? The first question is, how does allowing the intercept to vary give you a fixed effect estimate where you use only the within individual level variations, okay? So let me repeat myself. The first question is, how does allow intercept to vary, which means on the individual level, give you a fixed effects estimates where you use only within variation? Generally speaking, there are two ways to think about this intuitively, okay? The first one is procedural, more like, the way you do it. By allowing the intercept to vary, it is sort of like we are adding a control for each person. Let's take a study of countries, for example. But if India is in our example, then one of intercept is going to be beta 1 India, okay? For the beta India for the for that specific country. This intercept only applies to India, not to any other countries. If it's talking about China, then it's going to be China. That's a lot like adding this is India binary control variable to the regression, like a dummy control variable, and then beta India is the coefficient on that control variable. We have one of these controls for each country in our data, so we are controlling for each different country specifically. And we know that what happens when we control for country, we get the within country variation controlled. It's a fixed effects on country level. The second way to think about this question, like how do we deal with intercept for giving you a fixed effects estimate when you use within variation? Second way to think about it is that why this works intuitively to think of graph, okay? So if we use data on GDP per capita and life expectancy from the Gapminder Institute, here's how we isolate just two countries, like India and Brazil, for example. We look at their data since 1952. So what's going on here is that we have sets of data for India, we have sets of data for Brazil. We are looking at the question of GDP per capita and also life expectancy in two countries. So what we measure is that how does country's wealth level have to do with life expectancy on average in that specific country? So what do? We observe two countries, India and also Brazil. Brazil is is statistically, I guess, richer than India. So even looking at they are actually in different regions, okay, in terms of economic prosperity. Like India is to the left of the GDP per capita log scale row. I mean not row. I mean x-axis, and then Brazil is to the right. So we can see a few things clearly in this particular figure. Things in both countries are clearly getting better over time. Like moving from 1952 to 2002, 50 years, things are getting better, improving, supposedly. However, there are some clear between country differences we want to get rid of. And that regression line with a single intercept for both is clearly underestimating the slope of the line that each one of the country have. So if we break this intercept, we then instead use two separate lines, okay? Parallel lines, since they have the same slope, and we move them up and down until we hit each country. This lets us not care how far up and down each country's cluster points is, since we can just move them down to hit it, okay? And then with that, that lets us not care how far right each country clusters, since by moving up and down, the same slope can hit the clusters to no matter how far out to the right it is. We get within variation on the x-axis variable. That's even if it is moving left, that's also perfectly fine. And as a result, we have within variation. Okay. So to look at it more closely with a to connect the dots, connect all of the dots, we can have the same slope, but with different intercepts. This is what we're trying to say. And then the lines are a lot closer to the points now. These lines capture relationship that's clearly there's a lot better than the single regression line itself. Okay, so instead of doing the fixed effects, it's actually going to be having multiple regression lines drawn hypothetically. All right. So now the second question that comes up is that how do we actually estimate the regression with individual intercepts? Okay. Again, we have a bunch of ways to do that. First one is to extract the within variation, work with that, calculate the mean of a dependent variable for each individual, subtract that mean. You do the same for all the independent variables, then go back to the regression. This is called absorbing the fixed effects approach. Okay. There's an example of doing this. We actually can try that in a little bit, but I kind of want to go through the whole thing first, and then we can have you run it through. I think that will be good. Okay. Then the second simple method is to add a binary control variable for every country, which is individual level data. Or rather, every country except one in our model has an intercept constant in it that including every country will make the model impossible to estimate. So we leave one out or leaving the interceptor out. That one left country is still the analysis, but it doesn't get its own coefficient. It's just that it's stuck with this lousy constant, and then you do this automatically. You use that as a baseline control group, okay? And then you always compare that specific country to a different one. So with those two approaches being introduced, the second one is not oftentimes what we would actually go for, because including a set of binary indicators in the model it's okay when you have like a few different categories, but if you're controlling for each individual, you might have, I want to say, hundreds, if not thousands of them controlled. So this can get very, very, very slow. And when you're really doing the intercept then that's going to be pretty lousy. So but we're going to try out this using the R codes, and then look at the R outputs, and then again you estimate a bunch of country coefficient, but these are on the table. There's just a lot of them, so you can look at that. So all right, let's see if wow, this is still restarting, so I think there's something wrong with it. I'm going to close the window, don't save, and then I'm going to reopen it in a little bit. Okay. The third question is just going to, I'm almost there. The third question is just like when you interpret the results of regression once we estimate it, a couple of things, okay? The slope coefficient in the fixed effects model is the same as if you control any other variable within the same value of the country. How is variation in log GDP per capita related to variations in life expectancy? So I'm just going to highlight this just so that I can't highlight it here. It's not editable. But keep in mind, this is the same as you were to explain the other coefficient when you control for any other variables. But you have to add this, like within the same value of country, the variation in log GDP per capita related to variation in life expectancy. Put it the other way, okay? Since we have a coefficient, if we have a coefficient of 9.76, we can say that for a given country, in a year where the log GDP per capita is 1 unit higher than it typically is for that country, then we can expect life expectancy to go close to 10 years longer than it typically is for that specific country. All right? But from the table, there are more than just the coefficients that you can observe. You can see that there's R-squared value quite different in the two columns. Why is that? Because the R-squared is a measure based on how much variation there is in our residual relative to our independent variables. In the first column, when our dependent variable is just life expectancy within, then not life expectancy, then the R-squared is based on how much variation there is in the individual relative to the within variation thing. Okay, not the overall variation of life expectancy in general. So this is what we call the within variation R squared, or you can just call that within R squared. On the contrary, the next column tells us how much variation there is residual relative to all the variation life expectancy, and it counts part of life expectancy explained by between variation as well. Okay, so if we look at the fixed effects themselves, okay, something that's not on the table, coefficients we got in the second regression. Then the intercept in the specific fitted line, we can use that specific intercept minus that absolute terms, and that gives us what we call the comparison or the differences of these two countries. Like, we can say that India's is higher than life expectancy is higher that many years higher than Brazil's in general. So if they both have the same GDP, then India has a longer life expectancy than Brazil. And then again, we're still looking at the effect of one variable controlling one another, but we're looking at the effect of country controlling the GDP per capita rather than the other way around. So that's it. And then the researchers oftentimes use fixed effects to estimate, to make claims about the individual being evaluated. You control the country level GDP, like, given India has especially high expectancy given its level of GDP per capita. So this can be like an interesting thing to look at differences between individuals when you control individual level differences. But keeping in mind, fixed effects is a good way of controlling a long list of unobserved variables that are fixed over time to look at the effect of time varying variables. Those individual effects don't have the same luxury of controlling for a bunch of unobserved time varying variables. We can rarely think of individual fixed effects estimates as causal. Very last set of things is that it focuses on within variation. So the treatment estimated with will focus a lot more heavily on people with a lot of within variation. In that life expectancy and GDP example, the coefficient on GDP we got is closer to estimating the effect of GDP on life expectancy in countries where GDP changed a lot over time. But if the GDP is fairly constant, you count less for the estimates. You can address this by using weights to address the problem. So that's even more. All right, so let me pause here for a second. There are more to this, but I don't think I'm gonna work on that. I'm gonna just have you run the data and see if you can actually make it work. So if you have the whole data set, you can we emailed it to you, and then you can open it up and then just start by packages causal data fixed set requires but not okay, I'm going to install them. Causal data fixed set GPs. Okay, so this means all of the modern summary PLM. Okay, I'm gonna install all of them. So this is something new I just learned. So when you load this R script, if you have data sets that are not being installed already, this is on Windows, it's actually going to have you install, it's going to remind you to install it automatically. And what I'm doing right now is that I'm installing all our packages: causal data, fixit, gplots, model summary, PLM. So all of them are installed right now, which is fantastic. Then my line 1 to line 3 doesn't need to be installed again. Okay, I did that because in my R packages on the MacBook at home, I don't really have those data sets. But what I just learned just now, as you can see, it automatically reminds you on Windows. This probably will do so on Mac too. I just probably have Mac. I'm still trying to catch on tricks of this. It reminds you to install it. You can click on, and then it just installed it right away. But remember, when you came in, it was trying to restart. which means I probably mess it up, okay? So, but I would, so that's it. Now, what I need to do is, let's see if this works. I just need to load the data. Okay, now, all right, so there's still going to be a problem because, let me see if I can do them separately. All right, I can do them separately. Don't do them in one line. Okay, there we go. That I can do. Okay, the next thing what I need to do is I'm gonna do the model as suggested. Two different models, measure the life expectancy using the GDP. I can do that. Okay, so I was able to do two models, a list of different elements. I can try that with a general model too, looking at different countries and also life expectancy and trying to look at the relationship using that and the wages. And also the life expectancy years. I highlight that, I can do that. Now, look at this. Line 18, because the data has already been loaded, I don't have to load it again, okay? I only need to recall the data set. That's it, okay? So let's say I don't even need to library the causal data because it's there already. So this is what I do with two-way fixed effects. Okay, now the two-way fixed effects actually works here, okay? If you would actually load the data first and do that, okay? Okay, it actually does run. All right, so that's everything up until line 27. That is up until line 27. That is what we had gone through testing the life expectancy following the examples, let's say life expectancies and GDP level. So those two questions, this one, looking at this data set, model summary, and also using the first method as well as the second method. Okay, what I have done is actually to take out the R codes for you and put it in one file and have you run it. Okay, so and figure out the life expectancy itself, okay? I'm gonna have you practice all the way through this particular library foreign thing. Don't do the library foreign thing as of yet. Just do everything above library foreign and see what you get, okay? And also see if you can get the, the install packages thing, like you don't have to install it, and see if that works, okay? I'm gonna have you practice. If you need to use the restroom to take a break or something, feel free to do so. But otherwise, it's your time to run them. Okay. If you run into a hiccup, feel free to talk to each other as well. Okay. Work in groups if you want to. I think it's better to help each other. Did you get the email from the department this morning? Okay, it's supplementary, one of the supplementary packages, okay? There is what I call the R file. Just download that. It's very straightforward, okay? Very straightforward. I'm just trying to look for what my boss sent me. If you choose to If you choose to do it later when you get home yourself, I'm not going to be I'm going to be fine with that too. But before you leave though, can you do us a favor and scan this code? Just fill in some good or bad words as you want about the use your phone to scan it. Put in a bunch of comments, and that's it. Okay. And then run the codes yourself. And if you have questions, come over and ask, and I'll be happy to help. Okay. But other than that, this is what I want you to run for the fixed effects models. Okay. Just run it. If you run into a problem, come and ask me.